How can digital twins help heavy machinery operators move from reactive fixes to predictive maintenance strategies? What role does digital engineering play in sustaining performance and reliability across the lifecycle of complex equipment? I'm Asma, Senior Product Marketing Manager at ANSYS, and you're watching the Twin Talks. To answer these questions, we are joined today by Bhaskar Banerjee, Lead Application Engineer at ANSYS. As an industry leader in the industrial equipment and manufacturing sectors, Bhaskar supports OEMs to identify opportunities to solve problems and align with their sustainability, innovation, and business goals. Bhaskar has been with ANSYS since 2022 and has previous experience at the Goodyear Tire and Rubber Company and Cummins. He holds a doctorate degree in NVH model correlation and updating and a master's degree in mechanical engineering. Bhaskar, thanks for joining us today.
Thank you, Asma.
My first question for you is, why is predictive maintenance such a critical topic right now for the heavy machinery industry?
So predictive maintenance is more than a trend. It is becoming an operational necessity. In industries like mining, construction, refining, downtime doesn't just affect performance, it hits the bottom line. A single hour of unplanned downtime in a mine or refinery can cost hundreds of thousands of dollars, if not more. Traditional maintenance strategies like run to failure or time-based schedules either respond too late or result in over-maintaining healthy equipment. So with predictive maintenance, we move to a more condition-based approach that is smarter and more cost-effective. By using simulations to understand stress, temperature, fatigue behavior, and combining this with real sensor data from the field, we can catch problems early. For example, in a mining excavator, pressure fluctuations in the hydraulic circuit can reveal early signs of seal wear or internal leakage. Instead of waiting for the failure to happen, the operator can schedule a fixed, planned during downtime. And there's more at play here. Supply chain disruptions can make spare parts harder to get. Sustainability pressures demand longer asset life, and safety standards are becoming stricter. So, predictive maintenance not only reduces downtime, it optimizes maintenance resources, extends the life of components, and creates a safer, more reliable operating environment.
And how does digital engineering reshape how OEMs and operators approach machine reliability and performance?
So, digital engineering allows us to simulate how equipment will perform in the real world before we build it. And that changes everything. It's like having a virtual test lab where engineers can push design to their limits, optimize structures, and understand failure modes, all without cutting any metal. So let's say an OEM is designing a new wheel loader. Instead of building a prototype and running physical fatigue tests, they can simulate dynamic loads on the boom arm, the stress concentration on the welds, and the fatigue life under repeated loading cycles. These simulations help the team make better decisions, whether it's adjusting wall thickness, weld position, or even manufacturing parameters. But the real advantage is that these models don't stop being useful once the machine is in the field. The same simulation model becomes part of a digital twin that can track real usage. Say the loader is used in harsh terrain or lifting heavier than expected loads. The digital twin adjusts its predictions in real time based on actual conditions. So this shift that we have seen from then approach of design and forget to design, validate, and continuously improve, OEMs gain faster development cycles, fewer field failures, operators get more reliable machines, and data-driven maintenance insights. That's the power of digital engineering, I would say.
Can you explain how digital twins go beyond traditional simulation in supporting real-time operational insights for heavy machinery?
So, talking about traditional simulation, it's static. It gives you insights at a fixed point in time based on an assumed boundary condition. It is useful during design and validation, but once the equipment is out in the real world, these assumptions often break down. Digital twins take simulation to the next level by linking those validated models with real time sensor data. This allows the model to evolve with machine's operating environment. So think of a gear-driven system used in, let's say, a processing plant. In simulation, we can estimate fatigue life under standard loading conditions. But what happens when the plant runs an extra shift or when the ambient temperatures rise unexpectedly? A digital twin of that same gear-driven system would take in real-time load, speed, temperature data, and adjust its predictions dynamically. If the vibration levels exceed expected thresholds or thermal fatigue starts to accelerate, the twin can flag it before a problem becomes visible. This gives operators early warning, time to investigate, and control over maintenance schedules. This capability is also critical for fleet-wide health monitoring. If you have 100 similar machines across multiple sites, you can detect common patterns, identify outliers, standardize maintenance practices. So the value isn't just real-time insight, it's actionable intelligence across, the entire operation.
And how are companies using physics-based and data-driven models together to improve prediction accuracy and performance?
That's a great question. So physics-based models tells you how a machine should behave, and data-driven models tell you how it is actually behaving. So physics-based models are built from first principles. They are grounded in material properties, boundary condition, laws of motion, thermodynamics, fluid mechanics, so on and so forth. They're great at predicting how systems behave in an ideal or controlled condition. But they struggle when real world variability kicks in, like wear or dirt accumulation or operator behavior. That's where data driven models come in. Machine learning can analyze historical telemetry from sensors and find hidden patterns, things humans or even traditional models might miss. It can adapt to new conditions and learn from what's actually happening in the field. So by combining both, companies are getting the best of both worlds. For example, in a forestry vehicle drivetrain, the physics model simulates torque loads and gear stresses under different conditions. But in field, muddy terrain and operator aggressiveness can introduce load spikes that weren't part of the original assumption. A data-driven model trained on real telemetry detects these patterns. The hybrid model plus the physics data adjusts its fatigue prediction based on the actual usage. The result is higher prediction accuracy, better reliability planning, fewer surprises, and because the model explains why something might fail, it builds trust with engineering and operation teams alike. So I feel that is this trust is key to a successful deployment.
And how do digital twins support the full life cycle of heavy equipment from design through sustainment?
So one of the most valuable things about a digital twin is that it's not just an operations tool. It adds value across the entire life cycle of a machine. During design, it can help engineers simulate and refine performance under expected use conditions. You can explore different design configurations virtually, run fatigue analysis, make smarter decisions on material and geometry before prototyping. In manufacturing, the twin acts as a reference for quality assurance. You can compare actual build metrics to model predictions, checking if tolerances, clearances, or balance meet the simulation balance. Once in operation, the twin shifts to a live monitoring role. Take in data from sensors to track health in real time. For example, a concrete mixer truck. It can monitor vibration, load cycle, and stresses on the drum. This helps predict when the drum is nearing fatigue limits. At the end of the life or during service planning, the digital twin becomes a historical record. You can see how many cycles a part went through, what loads it experienced, how was it maintained. This helps you decide whether to refurbish, retire, or reuse some of the components. So the big benefit, you're not treating every machine the same, you're making decisions based on how this machine has lived its life. So this level of insight lowers cost, extends life, and obviously improves safety.
Bhaskar, what advice would you give to OEMs or fleet owners just starting their journey with digital twins and predictive maintenance?
Start small. Don't try to boil the ocean by modeling the entire machine down to every fastener. Focus on a critical component where failure has a high cost or a safety risk, like a gearbox, a hydraulic actuator, or an electric motor. For example, one customer in a refinery faced recurring failures in pumps and motors. We built a digital twin combining physics-based simulation and sound recordings from the field. This helped detect issues like motor eccentricity, shaft misalignment, and even gas leaks long before they became catastrophic. What made this successful wasn't just the tech, it was the focus. The team picked a clear problem, had good quality data, and ensured simulation and operation teams collaborated closely. So if you're just starting out, identify a use case with real business value, get early wins, and scale from there. Align your teams, validate your models, and keep asking, what decision can this twin help me make better? And that's how twins become more than a buzzword. It becomes sort of a business enabler, if I may put it that way.
Thank you so much, Bhaskar, for being part of this new Twin Talk episode.